Okay, chapter 13 is basically revision here, okay? Sample space and probability. You know this page, I just keep changing like the order of the lines, and I keep using for year 9, year 10, year 11, and year 12 students. I've changed it for 4 years already. So that's from year 9, okay? So you learn this, which means you learn this from year 9 because you were at the school from year 9, okay? Year 9, year 10, year 11, year 12, exactly the same. Okay, what is talking about? So sample space probability, I don't really want to repeat all of this. What is probability? Probability is number in between 0 and 1. What is a trial? Trial is an experiment. What is an outcome? Outcome is the possible results from this experiment. What's a sample space? Sample space is a collection of outcomes, is a set. Okay, it's a collection of outcomes. And what is an event? Event is some favorable outcomes. For example, I said I want a head for toss a coin, so getting a head is my favorable event. That's an event. Okay, equal likely outcomes. So you have all the outcomes have the same chance of occurring. Okay, not all of the experiment will have that. Okay, so only for throw the dice, toss the coins. You cut the circle into even pieces and you do the spinner game, so they are equal likely outcomes. Okay, the outcomes of an event in which outcomes are equal likely, you find the probability by probability, the number of favorable outcomes divided by total number of outcomes. That will be the probability. And we have subject probability. You don't need to know much about it. Subject probability is what you think the probability will be. There's no really evidence, or it's not really a fair probability. It's just based on what I'm thinking about. I think you have 90% of the time can win the game. I just believe that. Okay, there's no evidence. So that's a subject probability. And okay, according to that, we have experimental probability. Experimental probability is based on evidence. I do the experiment for a lot of times, and I find the probability by using the result of the experiment. Okay, and the long run proportion. You know the theoretical probability for tossing a head is a half. Okay, theoretical, that's theoretical. But when you toss a coin 10 times, you're not necessary to always get 5 heads. You can have like 1 head and 9 tails. So your experimental probability will be 1 on 10, but the theoretical is 1 on 2. What's the difference? What is the difference? Well, you know they should be the same. So this is the long run proportion. When you do an experiment for infinite many times, you just keep doing, the probability you achieve in the end will get approach to this theoretical probability. Okay, when it's infinite number times of experiment you have done, the probability will closely approach to theoretical probability. Okay, that's all definitions you have learned before, and we have what is probability. Okay, probability A must be greater or equals to 0. Probability of an empty set is 0. Probability of the union set, which is like this means the total outcome, so which is 1. So the sum of probabilities of all the outcomes will be 1. So probability A dash equals to 1 minus probability A. That is like complementary probability. Okay, some 3 formulas which is really important here. Probability A union B is A plus B minus A intersects B. Okay, and the next one is mutually exclusive. Mutually exclusive, what's the mutually exclusive? Mutually exclusive means there's no the thing can't exist like in common, like you can't exist together. Say, for example, I will wear black and you wear red, and we can never wear that together. That will be a mutually exclusive event. So the thing can't occur at the same time, okay? The thing can't occur at the same time. That would be mutually exclusive. Okay, so you use this formula, probability A intersects B equals to 0, to test whether this is a mutually exclusive event or not. Or if they ask you to reason whether this is a mutually exclusive event, you will say, oh, because this intersects that equals to 0, so they are mutually exclusive. Next one is independent. It's all definition here. Okay, independent. Independent will be A intersects B equals to probability A times probability B. Independent events means the occurring of events B doesn't affect the probability of A occurring. So it doesn't matter B happens or not. A will always be that occur, is always that probability. Can they have intersections? Yes, they still can have intersections. They can happen each other. For example, the probability you wear red, I wear black. Okay, it's independent events. We are not influencing each other. Whatever I like doesn't influence on what you like to wear. But we can have intersection. We can wear red and black together. So that is independent, but independent can also have intersections. Okay, independent events also have intersections. Okay, so the formula, the original formula we do is this one. Okay, with reasoning is this one. Is the probability A intersects B equals to probability A. This formula means the occurring of events B given, like, I want to find the probability A happens, given that B already happened. That probability is still equals to the probability of A occurring, which means the B doesn't really work for A, like not really influencing on A. So this is the original equation for an independent event, okay, for an independent event. And if we just expand the formula, that's probability A intersects B divided by probability B equals to probability A, and then we times on both sides. So probability A intersects B equals to probability A times probability B. So that's how the first formula come from. But like we use this a lot, okay, we use this more. We're not really using this one. This one is just the concept, and then we expand the formula to get this one. That's how we test it. That's how we test it. Intersection. Again, another question is, do you think mutually exclusive events and independent events will happen at the same time? I said this event is mutually exclusive already. You know, like events A and B are mutually exclusive. Do you think they are independent at this as well? Do you think they will be independent as well? Or say A and B are independent events. Do you think they are mutually exclusive events? Or do you think they really have an influence of each other? Mutually exclusive and independent? No. Okay? There's nothing like connect them together. Like when you see the two things, oh, one is have no common set, and then you think about, oh, maybe they are independent because they're not really in common. As I explained, independent events can have intersection. It doesn't mean they have no intersection. They have intersection. But mutually exclusive events means there are two separate like circle in the Venn diagram. They have no intersection at all. So they are different. Okay, they are different. So mutually exclusive events doesn't equivalent to independent. Independent doesn't equivalent to mutually exclusive. You can't think they are the same thing. Or in other words, most like 99.9% of the time they are not the same. They can't occur at the same time. They can't occur at the same time. If it's independent, it's not going to be mutually exclusive. If it's mutually exclusive, it's not going to be independent. It will be like that. Okay. That's this one. And the last one, there's another formula here. You don't really need to work out, like think about that, but like better know it. Probability A equals to probability A given B times probability B plus probability A given B dash times probability B dash. Okay, that's called total law of probability, law of total probability. Like this is something what I learned in uni before. I haven't really learned this in high school, and I can see this formula. It doesn't really, well, in uni you really use this formula a lot, but like in high school we don't really use it. This is equivalent to tree diagram. Every time you can use this diagram, this formula, it will be equivalent to a tree diagram. The tree diagram can help you to solve for this type of probability questions. I'll show you an example below here. So what this formula means, I want to find the probability of A. I will first find the probability when B happens. what's the probability A will happen, and I'll times the probability of B happening, and plus I will find the probability B is not happening, and what's the probability A happening, times the probability of B not happening. Okay, that's the total law of probability. That's exactly a tree diagram. I'll show you here. In a certain time, the probability that it rains on any Monday is 0.21. If it rains on Monday, then the probability that it rains on Tuesday is 0.83. Okay, I'll give you, say, M means rain on Monday, and T means rain on Tuesday. Okay, can you use a mathematical representation to help me to represent the sentence? If it rains on Monday, then the probability that it rains on Tuesday is 0.83. Just PR what equals to 0.3? I don't want a sentence, I want a math equation. Rain on Monday, given if it rains on Monday, then the probability it rains on Tuesday is 0.83. It's definitely a given question. It's definitely given. Who give which given which? Is T given M or M given T? T given M. Okay, so we have probability T given M is 0.083, and the probability of M is 0.21. And the next one is if it does not rain on Monday, then the probability of rain on Tuesday is 0.3. So it's still probability of T given M dash equals to 0.3. Okay, given M dash equals to 0.3. So now I want to find the probability on both Monday, rain both on Monday and on Tuesday. Okay, what do you think the probability will be? I want the probability rain on Monday intersects Tuesday. What that equals to? Or you can just purely think from the question. You don't really need to think about the formula. Okay, what's the probability will rain on Monday? 0.21. So the first number must be 0.21. Intersection means times. What's the probability will rain on Tuesday as well? Do you take 0.3 or 0.83? 0.83, because already know Monday is raining. Okay, already know Monday is raining. So you times 0.83 here. So 0.21 times 0.83. If you can't see it, I will draw a tree diagram for you. I said this type of question is tree diagram question. So I have Monday rain, Monday not rain, Tuesday rain and Tuesday not rain, Tuesday rain and Tuesday not rain. Monday rain is 0.21, Tuesday rain, Monday not rain is 0.79. If Monday rain, Tuesday rain will be 0.83. If Monday not rain, Tuesday rain is 0.3. Then this will be 0.7, here will be 0.17. That is just a tree diagram. Okay, all the information given to you is just a tree diagram. And I want Monday rain and Tuesday rain is the first outcome. So it's 0.21 times 0.83. I can't see my screen. Okay. That's A. And B. B is the probability rain on Tuesday. So I want to find the probability of T. That will equals to probability T given M times probability of M. Using the law of total probability and plus probability of T given M dash times probability M dash. That's the total law of probability. Probability of A equals to A given B times B and A given B dash times B dash. That is 0.83 times 0.21 plus 0.3 times 0.79. Because probability M dash will be 0.79. Okay, also you can see from the tree diagram, Tuesday ring means you can Monday ring plus Tuesday ring, or Monday not ring, Tuesday ring. Those two outcomes, it will be the same. It will be the same. If you can't remember the total law of probability, you can use tree diagram to help you. You can still work out the answer. That will be identical. Okay. Next one is 3 tools to help us to work out probability. We still use those 3 even though we learn more complex probabilities. Venn diagram, tree diagram, and the Carnot map. So, okay, the important order will be number 1, number 2, and number 3. You must know a Carnot map, you must, then you will know a tree diagram, and then you list, we don't really use Venn diagram. So, number 1, number 2, number 3 is in a reverse way. Tree diagram. I will show you one question later after we finish all the probability. That question you think is not making sense at all. You don't know where to start. But if you can start to try tree diagram, that will make much sense. Okay, so the tree diagram. After you think about, nothing can work here, try to think about tree diagram. It can be quite helpful. Okay, and this kind of map, you know that, you add vertically and you add horizontally, they need to all give you the same number. Let's have a look at, this is a VCAT question. Okay, this is exactly a VCAT question. This is, I think it's a 3-mark question if I'm not remembering wrong. You just need to use Carnot map. Okay, if you know this, the probability table, or you can call this a probability table. If you know that, you can work out that. 2 events A and B from a given event space such that probability A is 1/5, B is 1/3. Calculate A dash intersects B. Given A intersects B is 1/8. So I need to set up the table. Okay, A dash, B dash. And I know the value intersection is 1/8. Probability A is 1/5. Probability B is 1/3. I want to work out A dash intersects B, which is this one. A dash intersects B, which is this one. So I just use 1/3 to subtract 1/8. That is 5/24. You don't really need to complete the full table. You can just do what is asking. Okay, next one is calculate A dash intersects B when A and B are mutually exclusive events. Okay, mutually exclusive events. Okay, I don't like to see we are learning math. We don't want to see things in words. We want to change that to math representations. So when you see mutually exclusive, what that means? It means probability A intersects B is 0. That is something you at once needs to write. Even though you don't know how to do this question, you write that, you get marks. Okay, you just changing the word into math and you will get some mark for probability. So make sure you're changing all of that. Okay, first, that's the first thing you need to do. And next is just, I still have the same table here. I still have that table here. I have A, I have A dash, I have B, I have B dash. And that point is 0. And I still have 1, 3, and 1, 5. I want A dash intersects B. I'm still working for that one. So that is a third. It's just a third. It's a third minus 0. Okay, see, that's weaker question. They're not hard. They are really easy. There are some questions just give mark to you. Okay, if you know the table, you can get the mark. Okay, next thing. Next exercise, it will be more serious. You have learned this in year 11 as well. It's about chapter 10, or I think it's chapter 10 in year 11. Discrete random variables. Okay, discrete random variables. So, what's that? Okay, random variable. It is one whose value is determined by the outcome of a random experiment. Okay, so random variables are numbers. What you can get is only numbers. Random variable, this thing can vary from numbers. This can be 0, can be 1, can be 2, can be 3. It's not going to be, I have, for example, a family born 3 baby, and you have girl, boy, boy, girl, 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 boy, girl, like different outcomes. You're not really talking about the outcomes. You're not describing the outcomes. You're using number to represent the outcome. For example, if I let the number of girl become the random variable, then you can have 0 girl, 1 girl, 2 girl, all 3 girl in this family because there are 3 kids. You can have 0, 1, 2, or 3. The number of girls can vary depend on different outcomes, like how the mom get this baby. So that is something vary. That's why it's called the random variables. So there are 2 different types of random variables, discrete and continuous. So that's the 2 different things we learn in year 12. Okay, we have one set is discrete and one set is continuous. We'll learn continuous later. Random variables are expressed as capital letter. Okay, that's some notation thing. Capital letter. When you see something, when you want to say, okay, the letter X is a random variable, then that must be a capital X. If you want to say, okay, C is the random variable for the number of cats in this house, you will have capital C to represent that. So it's all in capitals. And their value they can take will be represented by lowercase. So basically you say the probability capital X equals to lowercase x, which means the random variable is X, the value it takes is lowercase x. Lowercase x means a number, a particular number. Like x equals 1, equals to 2, equals to 3. The capital X is not a fixed value. The x can be varied. 0, 1, 2, 3, 4, 5. Okay, can change. That's the notation thing. And what is a discrete random variable? That's something is countable number. Okay, for example, the number of white balls in the sample size, and we have children in the family, person's shoe size. Okay. Person's shoe size, you can have, for example, 35, 35.5, 36, 36.5, like until maybe 43, like stop here. I start from 35, stop 43, have 0.5 in between. It's still countable, okay? The shoe size is countable, like I have 1, 2, 3, 4, 5. I can list them out. That's still discrete one. So what is continuous? Continuous, the one can take any value in an interval for the real number line, and it's usually but not always generated by measuring. So like height, like weight, and the time taken to complete the puzzle, and all the examples, they are all examples of continuous random variable. So height, we normally just say, I'm 165, you are 175, or 171.2. We won't say the next decimal, but actually you can have the next decimal, you just not really measure it, like we directly rounding that up or rounding that down. So it can be, you can be 171.221, like it's still possible, or you can take any number in between, maybe 1 meter to 2 meters, okay, any number in between 1 meter to 2 meters. That's this continuous, but be careful, there are another type, let's say, just give you an example. Height of a person is continuous. But I will say height of a person correct to 1 dp. That's discrete. Because now you can list them. 170, 170.1, 170.2. Well, even though there's a lot, I can still list them all out. So it's not when I say height, it's all continuous. It depends on the case. If it's like just the height of a person, it's continuous. If I say it's a height of person, I want to correct it to 1 decimal places, then it will become discrete. Okay, it's different. Okay, next one. Discrete probability distribution are normally described in 2 ways. One by a table, well, I would say maybe 3 ways. There's another way by a graph as well. Or by a graph. Well, it doesn't really matter because it's quite like, not quite often to have a graph. So it's normally by a table. Table is the most, like they appear the most, and function is second, and the graph. So what is a table? That is a probability table. Okay, and I'll say what's this table represent? The random variable x. X is a value can vary between, can vary from -3 to 1 to 5 to 4. Okay, can vary between those 4 values. That's a random variable. Like that's what's the value I can get, and the probability of getting it will be 0.3, 0.2, 0.4, and 0.1, respectively. Okay, the probability, yep. Let me have a think. I need to have a look at the book. Well, I think it's a capital X on the top. I think it's a capital X on the top. PR capital X equals to lowercase x. That's true. Well, it can be a lowercase x, which means the value is -3145. Let's just have a look at the book. Just have the book here. Three. Just take example here. Because when I type it, I'm not really look at the book. I'll just type it. It's not this exercise. It's this exercise. It's lowercase x. It's lowercase x on the top, and then capital X equals to x later. Okay, it's lowercase because up represent the value it actually can be. So it can be negative 3, 1, 4, and 5. Okay, it's the value it can really take. What is it? And uppercase X means the random variable X equals to the value on the top. So it's capital X equals to lowercase x. So that's by a table. Well, I'll talk about more like how it can become a table later. Number 2 is by a probability mass function. So I can say it's not given a table. The advantage of a table is I can see directly what each value can take. It's very obvious. But the function will be a little bit less obvious. Well, I will say probability x equals to x is 1 over 4, 5 plus 9, 14. Let's say 1 over 14 x squared. And then I'll say x can belongs to 1, 2, and 3. Okay, so this is a probability mass function. If you want to know the probability capital X equals to 1, I just need to sub 1 into this function is 1 on 14. So the probability of getting 1 is 1 on 14. I can still convert that into a table because I can list that out in a table. Like 1 have probability 1 on 14, 2 I get the probability 4 on 14, 3 I get the probability 9 on 14. I can still change that back to a table. Okay, change that back to a table. And number 3 by a graph. If it's a graph, okay, I'll just convert this one into a graph. I can have negative 3. It's not. 1, 2, 3. 1, 2, 3, 4, 5. Okay, I can take negative 3. I can take 1. I can take 4. I can take 5. Okay, this is my x, lowercase x. That's my probability x equals to lowercase x. So I can have probability 0.3. 1, 2, 3, which is here. That's the probability 0.3. Have 0.2. 1, 2, which is here. Have 0.4. 1, 2, 3, 4, which is here. And have 0.1 for that. So that's how I represent by a graph. I can just read it from the graph. Okay, that's a discrete random variable distribution as well. We call this a distribution because, well, like this is how the probability has allocated to each values, how it can be distributed between each values. Okay, that's a discrete probability distribution. Okay, all of these 3 are represent the same quite similar things. Okay, what x can take, what the probability can take. You don't really need that one. That is true, but like you don't really need to use that to test. So, okay, I can't just randomly sketch a table and randomly put numbers in and that can become a probability distribution. That doesn't work. So the conditions for discrete probability distribution will be those 2. You need to test those 2. So first, each probability needs to be in between 0 to 1. Okay, that's very important. There's quite a few questions in VCA ask you to show this is a probability distribution. So first, I need to say or show all the probabilities are in between 0 to 1. You can't have probability greater than 1 or negative. Second, you need to add all the probability up and say that's 1 because the probability of the whole sample set will be 1. So you need to add them to show it's 1. Therefore, Okay, see this table. See this table. Have 0.3, 0.2, 0.4, and 0.1. They're all the same. Okay, they're all the same. Second, I add them. They're all in between 0 to 1, and add them. 0.2, 0.3, 0.5, plus 0.4, 0.9, plus 0.1, 1. So I added, and that's a 1, which means it is a probability distribution, which is the probability table. Okay, this one is a good one. Okay. An example of how to show a probability distribution table, or how to make a probability distribution table. Tossing a coin 3 times. Okay, let X be the number of heads obtained. Set up a probability density table or probability mass table. Okay, I'll draw a tree diagram first. I can have tail, head, tail, head, tail, head, tail, head, tail. That's the third outcome. Head, tail, head, tail, tail, head. And there's 8 outcomes. Okay, there's 8 outcomes. Each outcome will have 1/8 of the probability. Okay, 1/8 of the probability. Now, your random variable is X, capital X. The X is the number of heads you can take. Okay, we can have X and probability X equals to X. That's what we will have. And could you please tell me what X can take? Like what X is vary from? 1, 0. Okay, as well. You can have no head, 1 head, 2 heads, 3 head for toasting 3 coins. Well, can't have 4 head for sure because it only toasted 3 times. And you can have 0 for sure because you can't, like all tails. So I have 0, 1, 2, and 3 above. Okay, let's have a look at each outcomes. What X do you think it will be? Let's say that's a X for each outcomes. Okay, in the first outcome, how many heads you have obtained? First outcome, 3. Second, next, 1, 2, 1, 1, last one, 0. Okay, so each of these outcomes get a probability 1/8 to get. So to get a 0 head is 1/8. To get 3 head is 1/8 because we only have the top and the bottom one is 3 head and 0 head. Okay, how many cases you have 2 head? 3. So it's 3/8. And for 1 is the same. There are 3 outcomes to get 1 head. It's 3/8 as well. So 3/8 of the probability to get 1 head, 3/8 of the probability to get 2 head, 0 head is 1/8, 3 head is 1/8. That's how do we do that. Okay? Okay, if you finish that one, have a look at example 2 and to think about which one is actually a discrete probability distribution. Like I said, I can't all the table become probability distribution. If it represents probability, No, like it's not a multiple choice. You just test each one and tell me yes or no. It's not a multiple choice, okay? D is no. Why D is no? Okay, that's obviously negative, so D is not going to be. C is no, Y no. Okay, you add them 0.3, 0.6, and that's only 0.9. So that's not going to be. How about A and B? A, yes. B, yes. Okay, A and B, yes. C and D are no. Okay, example 3. Example 3. I want to find the value of K. Okay, for the first one, what K equals to? You can tell me at once. Okay, K is 0.2. Okay, how about the next one? Okay, you add all of that. That's how many K? 20K. 20K equals to 1. K is 1 on 20. Okay, or say 0.05. Okay, C. I'll give you 1 minute to calculate C. Well, you can use calculator if you like. Well, you can use calculator. That's fine.
Let's just do it.
You can try hand approach. Let's beat the calculator.
Okay, that's too hard. It's too. I'm having quadratic, but it's too fast.
Okay, what to answer? This is a quadratic. It's very likely to get two answers. So what K equals to? Or 0.4. Okay, thank you. Okay, will that both be your answers? Don't forget your two conditions. What's the two conditions? You only satisfy one because they add up to 1. Yes, you satisfy 1. What's the another one? In between 0 to 1. Okay, let's substitute the value in. Sub 0.1 in. Okay, 0.1 is positive. That's positive. That's 0.27. That's fine. And last one, 0.02 plus that is fine. Let's sub 0.4 in. K squared is fine. How about the second one? 0.3 minus 0.4 minus 0.1. That is not going to be the solution. Okay, you discussed your answer first because when K equals to 0.4, 0.3 minus K equals to negative 0.1, which is less than 0. So K will be only 0.1. You need to make a discussion. Okay. I want you to show you one example for the function. Okay, for the function. How do we show that like a function? This is a probability function. So show that px equals to 1 on 42, 5x plus 3, where x is 0, 1, 2, 3, is a probability function. Okay, Prx equals to x is equivalent to lowercase p, lowercase x. They are the same thing. Okay, PR capital X equals to lowercase x. That's the same as lowercase px. So we have P0. P0 is 1 on 40, no. P0 equals to, put 0 in, 3 on 42. P1 equals to 8 on 42, and that is divided by 2, 4 on 21. P2 equals to 10, 13 on 42. P4, no, not P4, P3. 15, 18 on 42. That is a 9 on 21. Okay, P0 plus P1 plus P2 plus P3 equals to 3 on 42 plus 8 on 42 plus 13 on 42 plus 18 on 42. That's 11 plus 31, which is 42 on 42. That equals to 1. Well, I will just directly write that equals to 1. Well, really test whether it's 1 or not, okay? Like sometimes maybe it's not. Just test it. Do not directly write 1. That's not enough. You need to give a discussion. So number 1, Px is in between 0 to 1 for x belongs to 0, 1, 2, 3. It satisfies the first condition. Second, the sum of x equals to 0 to 3 of Px equals to 1. So it is a probability function. Okay, so you say it is a probability. Okay, the sum means you add up all the probability starting from x equals to 0, finish at x equals to 3 for all the integer numbers. Okay, for all the integer numbers. Okay, so there's another 2. I'm not going to show that. B, you show that by yourself, and 5, you find the k value by yourself. They are identical questions compared to the top one. Okay, you just do that. I want to finish the last question, example 6, and we can start 13D next week, which we are not really behind it. Okay, example 6. A card is chosen randomly from a stack pack of 52 playing cards. A second card is then chosen randomly. Let X be the number of clubs chosen. Okay. What's the possible number for X? What X represent? Number of clubs you chosen. How many cards you have chosen? How many cards you select? 2. How many clubs you can have? 0, 1, 2. Okay, so you will see what you actually have done. You have to select 2 cards from this. You have 0, you can have 1, you can have 2. So now it's sure that X can be 0, 1, and 2. Okay, that's only 3 possible numbers you can take. Okay, construct a table of probability distribution for X if each card is replaced before the next card is chosen. It is replaced before the next card is chosen. So it's still the same 52 card the second time you have chosen. So how many clubs are there? Okay, let's do a tree diagram. That's only for A. Okay, what's the probability for the first time to get a club? Do you play cards? What's the probability of getting clubs? A quarter, okay? In every type of card, there's a club. So 1 on 4, okay? So 1 on 4. I'm really trying to teach. I play a lot. 3 on 4 is the probability of not getting that. It will be the same for the second time because the card you have select going back to this 52 cards, and it's still the same chance of getting that for the second time. So it's a quarter and 3 quarters. A quarter and 3 quarters. This is 1 on 16. This is 3 on 16. This is 3 on 16. This is 9 on 16. And can you tell me what's the x value here? For the first outcome, x equals to 2. First one, third one, last one, 0. Okay, now easily set up the table by using this tree diagram. Okay, x 0, 1, 2, probability x equals to x. Okay, get 0. I can have 9 over 16 of the chance of getting 0. 1, there's 2 outcomes getting 1. So it's 3 on 16 plus 3 on 16, which is 3 on 8. And 2 is 1 on 16. Okay, first one is easy because the probability are quite nice. It's either 1 on 14 or 3 on 3 on 4, 3 on 4. B will be without replacement. Okay. Can you let me know what's the first time will be the same, 1 on 4 and 3 on 4. Okay, the important thing is the second time. What happened for the second time? Okay, denominator decreased to 51 because 1 card is going out. What's the number of club left there? 12. Okay, how about this one? Like this is still 51. How many clubs not has been left in the card? What's my numerator? 30, 8 or 9? 9. Because there's no club not has been taken. The one you take is club. Okay, so you still have 39 out of 51 of not club. Okay. The next one, club. How many club has been left if the first one is a club not? 13. So 13 of 51. How about the last one? 38 over 51. Okay, you can find those probabilities. I know you can. The number of x is 2, 1, 1, and 0. And the probability of x equals to this, well, like you need to calculate that. I'm not going to calculate that, it's like too long time. You need to simplify that. For example, I can simplify this one. I can simplify that. I can simplify that. I can maybe I can not simplify that. I can simplify those two here. Okay, important thing is, the point I want to make here is I can use combination to do this. The NCR thing to do this question. Okay, I don't have enough time today. I'm going to finish up this next lesson, the first 5 minutes, but I want you to think about the NCR method. Okay, using the NCR method. For example, to get 2 clubs, I'll give you the probability x equals to 2. That will equals to, 52 cards, you select 2. That's the denominator. And the numerator will be 39, choose 0, and 13, you select 2. I'll give you this example here. You will try to figure out what is x equals to 1 and what x equals to 0. You don't really need to use the tree diagram. Save a lot of time. Okay, save a lot of time. I'll continue with that next lesson. You will think about that during your weekend.